two stones of masses small m and 2m, masses small m and 2m are wheeled in horizontal circles, are wheeled in horizontal circles. The heavier one in a radius r by 2 and the lighter one in radius r. It is found that tangential speed of lighter stone is n times that of the heavier stone. Tangential speed of the lighter stone is n times that of the heavier stone when they experience same centripetal force. When they experience same centripetal force. The value of n is option A 2, option B 3, option C 4, option D 1. Option A, that is 2, n equal to 2. See what is given in the question, that centripetal forces are same. So we consider that for two particles m1 v1 square by r1 equal to m2 v2 square by r2. Now consider 1 is denoting the lighter particle and 2 denoting the heavier particle. So their masses are m and 2m. So in place of m I can m1 I can write m. Its speed is given v. Okay. Then what is given? The lighter part 1 has a speed v. Tangential speed of the lighter stone is n times that of the value of the heavier stone. Okay, this one is nv. So this one is n times v and its radius of the lighter stone is r. Heavier stone's radius is r by 2. So this is 2m v square divided by r by 2. Now calculate. In the problem it is mentioned that two stones mass m and 2m, the heavier one in radius r by 2. So this is heavier one we consider, so its radius is r by 2 and lighter one in radius r, and then they mentioned that the tangential speed of the lighter stone is n times that of the value of the heavier stone. So if the value of the tangential speed for the heavier stone is v, then for lighter stone it is nv. And then from this equation calculate the value of n. So many things will cancel. M, R, and this v square will also cancel. So it will become n square equal to 4. So n will be 2. That is option A. Okay. Next question, write down. Question number 8. A stone tied to the end of a string. A stone tied to the end of a string of 1 meter long. A stone tied to the end of a string 1 meter long is whirled in horizontal circle with a constant speed. If the stone makes 22 revolutions in 44 seconds, if the stone makes 22 revolutions in 44 seconds, what is the magnitude and direction of acceleration of the stone? What is the magnitude and direction of acceleration of the stone? Okay. Option A, pi square by 4 meter per second square, pi square by 4 meter per second square, and directed towards the center, Okay. Option B, pi square meter per second square, pi square meter per second square, and directed away from the center. Option C, pi square meter per second square, pi square meter per second square, and directed towards the center. Option D, pi square meter per second square and directed tangent to the circle, See, number of revolutions is given. From that, first calculate omega. And then calculate centripetal acceleration by using omega square r. It is given that 22 revolutions in 44 seconds. Okay. So in 22 revolutions, how much angle is subtended at the center? 22 into 2 pi, because in one revolution total angle subtended at the center is 2 pi. So in 22 revolutions, the angle subtended at the center is 2 pi into 22, and that occurs in how much time? 44 seconds. So this one is in radian per second, and that is the value of omega. So omega is coming pi radian per second. Okay. Omega is coming pi radian per second. Now, centripetal acceleration is only acceleration present in this problem because it is moving with uniform speed. Since it is uniform speed, there will be no tangential acceleration, only centripetal. So this one is omega square r. So omega is already calculated pi, so it will be pi square. R is the length of the string. Length of the string is given 1. So it is pi square meter per second square. And as it is centripetal acceleration, it is directed towards the center of the circle. C is the correct option. Question number 10. A hemispherical bowl of radius capital R is rotating about its axis of symmetry, which is kept vertical. About its axis of symmetry, which is kept vertical. Full stop. A small ball kept in the bowl rotates. A small ball kept in the bowl rotates with the bowl without slipping on its surface. Without slipping on its surface. If the surface of the bowl is smooth, if the surface of the bowl is smooth and the angle made by the radius through the bowl with the vertical angle made by the radius through the bowl, radius through the ball, angle made by the radius through the ball with the vertical is alpha. Then find the angular speed at which the ball is rotating. Find the angular speed at which the ball is rotating. Option A, root over of g by r sin alpha. Root over of g, small g, by capital R sin alpha. Option B, root over of g by r cos alpha. Option C, g into root over of 1 by r cos alpha, means g by root over r cos alpha, g divided by root over r cos alpha. This one, g divided by root r cos alpha. Okay. Option D, g divided by root r sin alpha. G divided by root r sin alpha. The ball is somewhere here. Okay, somewhere here, and it is not moving, it is rotating. So this is the axis of the ball and it is rotating with angular speed omega, suppose. As a result, ball is here, not at the midpoint, because if it is not rotating, ball will be here. Since it is rotating, ball is feeling a centrifugal force, so ball will move up to this and here it stays. So you have to find this velocity for which the ball will stay here and it will not slip from this point. Okay, now it is said that this axis from this center of the hemisphere, if you draw a radius, it passes through the bowl at this position. This radius makes an angle alpha with this axis. This angle is mentioned as alpha. Okay. Now, first we want to draw the forces acting on the ball at this condition. See, First force is of course mg acting down. Second one is a normal reaction force along this direction, N. This one is mg. Clear? Now if we consider the reference frame of the ball itself, then it is non-inertial, because it is rotating means it experiences centripetal acceleration. So I will consider the non-inertial frame, that is the observer is on the ball itself. So when the observer is on the ball, he will again feel another force that is opposite to the direction of acceleration, that is the centrifugal force. So the centrifugal force is directed in this direction. Now why? Because ball is rotating in a circle like this. So its center of the circle is here, not here. Because ball is rotating in a circle smaller than radius capital R. Okay, so its center of the circle is here and it is feeling a centrifugal force opposite direction to the center, away from the center, and that is say m omega square small r, because we consider this circle in which the ball is rotating, its radius is considered as small r. It is not the capital R. Better I will not draw the entire circle, it will be too clumsy. I will just draw a single line. In a different color, I will draw this single line. So this is the radius, this is the center of the circle in which the ball is rotating. Clear? Now this entire radius of the hemisphere is capital R, but this is smaller than that. Now see the situation. At this condition the ball is at rest, means net force on the ball is 0 as viewed from the non-inertial frame. Okay, so just split the forces into component. So these two are already perpendicular, so don't split them into components, split n into components. How? One component of n is along this direction, another component of n is along this direction. If this angle alpha, this angle is also alpha. Then I can write n sine alpha will be here, and on this direction there is n cos alpha. So you can write from this n sine alpha by n cos alpha, that is equal to m omega square r divided by mg. Okay, because for equilibrium n sin alpha should be equal to m omega square r, n cos alpha should be equal to mg, so I divide both the equation. So n sin alpha by n cos alpha should be equal to m omega square r by mg. Okay. The two equations separately I haven't write, that is n sin alpha equal to m omega square r and n cos alpha equal to mg. You can write it for your reference. Then after that we are dividing these two equations to eliminate n. Okay. Now eliminate n, eliminate m. Now what is the relation between small r and capital R? So what is the relation between small r and capital R? See, this angle is 90 degree. So small r by capital R equal to sin alpha. So we can write small r equal to capital R sin alpha. Just substitute it here and write it as sin alpha by cos alpha equal to omega square capital R sin alpha divided by G. Okay, from that find omega. So this sin alpha will cancel. So omega square will be G by R cos alpha R cos alpha. So what we have done, the ball is at a certain height from the bottom position since the ball is rotating about its axis. So that's why the ball is experiencing three forces when viewed from the non-inertial frame, that is the frame of the ball itself. So the observer sitting on the ball will experience three forces. One is mg, second one is normal reaction, third one due to the acceleration, that is a pseudo force, that is centrifugal. So we consider three forces, n, mg and m omega square r. See, m omega square r and mg, they are perpendicular to each other, but n is oblique to them. So I want to resolve n only. One component of n is upward, that is n cos alpha. Another component of n is horizontally, that is n sin alpha. Then from that we can write n sin alpha equal to m omega square r, because when you view from the non-inertial frame, the ball seems to be in equilibrium from the non-inertial frame. So that's why we consider n sin alpha equal to m omega square r and n cos alpha equal to mg, and we divide these two equations to eliminate n, because I have no data for n. So after eliminating, you will get sin alpha by cos alpha equal to omega square r by g. Now here this small r is not the radius of the hemisphere, it is the radius of the circle in which the ball is rotating. Okay, so there is a relation between capital R and small r, that is small r equal to capital R sin alpha. Substitute that in this equation and you will get your answer. Now this same problem can be solved without using non-inertial frame. You can also consider that I am in the inertial frame and I want to solve the problem. Okay. Now in that case, if you view from outside, from the ground, the force on the ball are only two forces. One is n, another is mg. M omega square r centrifugal you cannot write, because you are now in the inertial frame. So what we will do, we will again split n into two components and write n cos alpha should be equal to mg, but there is one component n sin alpha towards the center of the circular path, and we will write that this force is unbalanced producing acceleration, and we will equate that with mass into centripetal acceleration, and you will get the same equation again. So you will consider now n sin alpha equal to mass into acceleration because of the Newton's second law. But whatever be, if you consider non-inertial frame, if you consider inertial frame, this equation will remain same. Only the logic on the explanation will be changed, but final equation there will be no change. Okay, so you can use any method, but it is generally advised to use non-inertial frame in this case, because non-inertial frame you can only balance the forces. and you can consider the body is at rest in the non-inertial frame. So it is much easier to apply the equations. Okay. Okay, now we will move on to the next chapter, work, energy, power. First, I will ask you one question. Tell me what is work done? Tell me what is work done?
Application of force on object.
So why it is work done? I can apply the force on this wall.
Zero.
So, but that is not the work done. Are you doing any work right now? No. Nothing. Physics says you are not doing any work right now. Because as long as the point of application of the force is not moved along the direction of the force, there will be no work done according to physics. So what is your today's work done? Zero. Okay. So first of all, work done is actually meant a process of energy transfer between system and surrounding. System to the surrounding and surrounding to the system. This is a process of energy transfer. Now mechanical work is described as if the point of application of the force moves in the direction of the force, then calculating the component of force in the direction of displacement and multiplying it by displacement, you can calculate the mechanical work. Remember, mechanical work. There are other types of work done. Non-mechanical types of work done, those are also present. But here we are only discussing the work done. So first of all, remember that if some object is some load is given to him, to anyone, and holding the load for a longer period of time at the same position, and after that his work done will be zero. But don't say. If a potter is carrying your weight, your bag and everything, and after everything you will say that I will not pay you any money because you are not doing any work. Okay. Question number part 1, level 1 questions. Question number 5. A uniform force of 3 I cap plus j cap Newton, 3 I cap plus j cap Newton acts on a particle of mass 2 kg, acts on a particle of mass 2 kg, and the particle is displaced from position 2 I cap plus k cap meter, 2 I cap plus k cap meter to position plus 3 j cap minus k cap meter. Means initial position is 2 I cap plus k cap, final position is 4 I cap plus 3 j cap minus k cap. The work done by the force on the particle is, the work done by the force on the particle is option A 9 joule, option B 6 joule, option C 13 joule, option D 15 joule. What? 6. 6 is option? How? Force dot displacement. So first you have to calculate displacement and then get dot product with the force. Don't pick up the options at your desire. First you have to calculate the displacement. Displacement S here is final position vector minus initial position vector. Okay. So final position vector is given 4 I cap plus 3 j cap minus k cap. Initial position vector is given 2 I cap plus k cap. So subtracting this means minus 2 I cap minus k cap. So it will become 2 I cap plus 3 j cap minus 2 k cap, and then take a dot product with the force. Force vector is given 3 I cap plus j cap. Okay. So it is coming calculate the product of the dot product between F dot S. That is the work done. So 3 into 2, that is 6, 1 into 3, that is 3, and then there is nothing, means k cap's coefficient is 0. So it will be 9 joule. How you got 6? Okay, next question. Question number 8. Velocity time graph of a particle of mass 2 kg. Velocity time graph of a particle of mass 2 kg moving along a straight line is as shown in the figure. Okay, here V is plotted in meter per second and time is in second. This is 20, this is 2. Work done by the force on the particle is, work done by the force on the particle is, option A 400 joule, option B minus 400 joule, option C 200 joule, option D 200 joule. Oh, option A 400 joule, option B minus 400 joule, option C minus 200 joule, option D 200 joule.
Option D, sir.
Why? Option D. Option D is 200. Options. Option A is 400 joule. Option B is minus 400 joule. Option C is minus 200 joule. Option D is plus 200 joule. Minus? Don't try to calculate force and force multiplied by displacement, because in that case first you have to calculate the area under the curve to find the displacement, then you have to take the slope of the curve to find retardation, multiplied by mass will give you force, then force into displacement will give you the work done. Use some other formula, work energy theorem. It will be much easier then. Work done by external force equal to change in kinetic energy. Final kinetic energy minus initial kinetic energy. Use that and it will come within a moment. Otherwise the answer will come, but you have to calculate. See, I will show you both the methods. First, the longer method. So this is coming 20 meter. Okay. Now what is the slope of this graph? 20 by 2, that is 10, but that is minus 10. Slope of the graph represents acceleration, but here velocity is decreasing, means it is retardation. So retardation A equal to minus 10, because 20 by 2 10 meter per second square. Then work done equal to force into displacement. Force means ma into displacement delta x. Then it will be m is given 2 into acceleration minus 10 into 20. So it is coming minus 400 joule. But no need to do all these calculations. Use directly work energy theorem. W equal to half m v2 square minus half m v1 square, where v1 is the initial velocity and v2 is the final velocity. Then what is v2? 0 minus half, mass is 2, V is 20, so it is directly coming minus 400 joule. Initial velocity is at t equal to 0, that is 20 meter per second. Final velocity at t equal to 2 seconds, that is 0. So I put V2 equal to 0 and V1 equal to 20, mass is 2. Then work energy theorem will directly give you the answer. No need to calculate the area under the curve, slope and all these things. Okay. Question number 12. The power supplied by a force, acting on a particle moving in a straight line, is constant. Okay. The velocity of the particle varies with the displacement x as option A, x to the power half, option B, x, option C, x square, option D, x to the power 1 by 3. It is D. Then how? Power delivered is constant. Okay? It means force into velocity, that is constant. Force into velocity is constant. Since it is moving along a straight line and force and velocity are along the same line, so in the dot product cos 0 will be 1. So I don't write the dot product on cos theta, I write directly F into V equal to constant. Now this F can be written as ma. So that is also constant. So we can also write A into V equal to constant, because mass of a particle is constant. Means acceleration into velocity, that is also constant, because any constant divided by mass is a new constant. So we write it constant. Now A can be written as V dV dx. There is another V, that is constant. Right? Now, can I write V squared dV? Now no more this constant I will write this constant K. Okay? So V square dV equal to K dx. Now integrate both sides. 0 to V, 0 to x. So it will become V to the power 3 by 3 and it will become kx. So we can write v equal to 3k whole to the power 1 by 3 into x to the power 1 by 3. So this entire term is a constant. So we can write v proportional to x to the power 1 by 3. That is the answer. So don't include t in the calculation, because if you include t, write a equal to dv dt, then again t has to be eliminated. So that's why I eliminate t from the beginning and write acceleration in the form of v dv dx. Because if t comes, then again finally you have to eliminate t. Okay. Because k is a constant, so 3k to the power 1/3, that is also a constant. So remaining portions are proportional. Write down. Question number 17. The potential energy of a particle in a force field is U equal to capital A by R square, capital A by R square minus capital B by R. The potential energy of a particle in a force field is U equal to capital A by R square minus B by R. Force field. The potential energy of a particle in a force field means under a force, gravitational force, or it may be any other type of force, where A and B are positive constants. A and B are positive constants and R is the distance of the particle. R is the distance of the particle from the center of the field. For stable equilibrium, the distance of the particle is option A, B by 2A, option A, B by 2A, option B, 2A by B, 2A by B, option C, A by B, option D, B by A. Question. The potential energy of a particle in a force field is U equal to A by R square minus B by R, where A and B are positive constants and r is the distance of the particle from the center of the field. For stable equilibrium, the distance of the particle is option A, capital B by 2 capital A, option B 2A by B, option C A by B, option D B by A.
So does it mean that R should be a constant too?
For a particular value of r, it is the stable equilibrium. But if you change the position, the value of r will change. Because suppose this is sun, and at a certain distance from the sun, it is a stable equilibrium condition. Then at other point, r may change. If r is a constant, then it will be a neutral equilibrium. So you know all the cases of stable equilibrium, unstable and neutral equilibrium. 2A by B, correct. Option B. See, first one thing, suppose this marker pen, if I put this marker pen here like this, okay, horizontally kept on the table, this marker pen. Now if I suddenly disturbed it from this position, first determine whether this marker pen now at equilibrium or not. It is obviously equilibrium because no net force is acting on it, because one force acting on it is gravity, another is the normal reaction given by the table, and they cancels each other. They are equal and opposite, acting on same body, cancels each other. So net force on this 0. Net force 0 means equilibrium. Now the characteristics of the equilibrium that we cannot judge from net force equal to 0. We can only assure that equilibrium means net force 0. But what is the characteristics of that equilibrium, that cannot be determined from the idea of net force equal to 0. Okay, now we have to check something else. I will disturb this marker from its position little bit. It will again come back to the same condition. I will again disturb it. See, again come back to the same horizontal position. Okay. Now that means if I disturb it from this particular equilibrium position, it will again come back to the same position. So it strongly urges to come back to that position. Now consider this situation. Again, what is the net force on the marker? 0. So it is again another equilibrium, but now we check whether it has the same characteristics as that of the previous one or not. You disturbed it slightly. Can it come back? So if you disturb it once from its equilibrium, it will never come back to the same configuration. So first one is the stable equilibrium. Second equilibrium is the unstable equilibrium. So from a stable equilibrium position, if you disturb a particle, it will again come back to the same configuration. From a unstable equilibrium, if you disturb the particle, it will never come back to the same equilibrium configuration. It will find the new equilibrium, that is it will go back to the stable equilibrium condition. See, if I disturb it, it will go back to the stable equilibrium condition. Now why this occurs? This is at rest, but its center of mass is here at a certain height from the table. So its potential energy, suppose mgh. Now it is also equilibrium, but where its center of mass now? At this point. So height of the center of mass above the table is very small, so it has low potential energy. So gravitational potential energy minimum means stable equilibrium, and gravitational potential energy maximum means unstable equilibrium. Because if you on the table, if in the body is kept on the table, that means the body is in contact with the table, and anywhere if you put this body such that contact is not loosed, then this is the maximum height of the center of mass, and this is the minimum height of the center of mass above the table. So minimum height of the center of mass means lowest potential energy, and this is the highest potential energy. So highest potential energy is always unstable equilibrium, lowest potential energy means the stable equilibrium. Clear? Another equilibrium is there. Suppose it is the stable equilibrium. Okay, this. If I rotate this body, it is also stable equilibrium. So every point over which the marker rolls, all the points are stable equilibrium. It will show no tendency to come back to the previous position again by rolling in the reverse direction. So every position is stable equilibrium. Why? Because if you disturb it from this position, at every position of its rolling over the surface, the height of the center of mass above the ground will remain same. So that configuration is called a neutral equilibrium. Neutral means, suppose a football, if you orient itself in any condition and kept on a horizontal floor, it will stay there. If you disturb it, will you say that I disturb it this much, so again after that it will roll back and come back to the same configuration? No, the disturbed condition is also stable equilibrium for it. So for every, because the center of mass of the football above the horizontal ground is not changing when the ball is rolling over the horizontal surface. So that's why all the positions are stable equilibrium. This type of equilibrium is called actually neutral equilibrium. Neutral means it does not matter whether you roll the ball over the horizontal surface, it is completely unaffected. But in first two cases, so there are three types of equilibrium. One is stable, unstable and neutral. Stable equilibrium, potential energy minimum. Unstable equilibrium, potential energy highest, maximum. And in neutral equilibrium, potential energy same at various positions. That is called the neutral equilibrium. So all positions are stable, then it is called neutral. Okay. Now, this concept, how this concept comes, I describe all these concepts on the basis of a physical experiment. But what is the mathematical analog of these concepts? The maxima minima calculation of the differential calculus. That is actually giving us this concept. Okay, so without a proper connection you cannot solve the problem. See, pause a little bit. Oh, take a 15 minutes break, and after that we will first discuss the mathematical analog of all this equilibrium, and then we will solve the problem in detail. Because if I indulge in the calculation, then it will take longer time. So first we consider any function. It may be algebraic function, it may be logarithmic function, it may be trigonometric, any arbitrary function. It may be x cube minus 3x plus 2, it may be 1 by x square minus 1 by x cube, like this. Now first, if I plot a graph of this any function, I want to plot this graph. So I don't know which type of graph it will show, so I will just consider an arbitrary graph. And let us consider the graph will be like this. It may have some other repetitions like this, maybe, so on. So I find this graph for any arbitrary function. Now we have to first find out the points where the tangent to the graph is a horizontal line to the x-axis. This is our x-axis. This is y-axis. Tell me how many points are there in the graph, as in between this graph. There may be some other points where also tangent may be horizontal, but they are not in the range that is specified in the graph. As this graph is presented in the board, tell me how many points are there where the tangent to the curve is a horizontal line, means parallel to x-axis. 3. So one is this point, one is this point, another is this point. So at these 3 points I can consider this. If I draw a tangent, that will be a horizontal line. This tangent will be horizontal. So what is the slope of this tangent line? 0. Slope of a tangent line means, straight line means dy dx. So dy dx 0 means line is horizontal. So at this point I can consider dy dx equal to 0. At this point also dy dx 0. At this point also dy dx 0. Now if I have that function, and this graph is arbitrarily given to you, but suppose a very complicated function is given to you, can you plot the graph easily? So in this graph we can see the graph and find out at which points the tangent will be horizontal. But if the function is very complicated and we cannot draw the graph, then we cannot say at which point the tangents are horizontal. Then without drawing the graph we have to adopt some other procedure. What? Suppose the functional form is given, y equal to say x to the power 3 minus x square. So don't plot any graph, just calculate dy dx. So it will be 3x square minus 2x, and set this dy dx equal to 0. Just put dy dx equal to 0. So I will write it in a different manner. Dy dx I will set this equal to 0, because we know from this that whenever the tangents are horizontal, dy dx will be 0. So I will set dy dx equal to 0 and I will find a equation. I will get a equation that is 3x square minus 2x equal to 0 in this particular example. Then we can say the value of x. Taking x common, I can write 3x minus 2 equal to 0. Means there are two values of x that I find, x equal to 0 and 2 by 3. So there are two possible values of x where the tangent to the graph will become horizontal. Clear? This is an arbitrary graph. If we plot this graph of this function, I will get 2 points where tangents will be horizontal. It may be a fourth order curve, means x4 is there, then we will get 3 points where tangents are horizontal. If it is a fifth order curve, means equation is fifth degree, then there are 4 points where the tangents are horizontal. Okay, it is a third order curve, so 2 points we find. If it is a fourth order curve, we find 3 points like this. Now, you may say that it may not be an algebraic function. It may be e to the power x sin x. Okay, that is a complicated function. For that, we will get many such horizontal lines. Now, these points in a graph where tangents are horizontal, they are named with a special name called stationary points. Means the graph that I describe here, this point, there is suppose certain x values of this point, x coordinate of this point. This point is a stationary point. This point is a stationary point. This point is a stationary point. Now, why then, how the name comes? Stationary points. What do you mean by the word stationary? Stationary means not moving. It is at rest. Now think of, suppose a mountain climber is climbing and reaches this point. So now if I ask you whether his climbing is complete, what you will say? Climbing completes to this point, peak, completes. Okay? Now, whether his downward movement begins? No. So, ascending completes, descending not started yet. So, what will be his condition now? Stationary. So, that's why the point is named as stationary. Now, same thing. Descending completes, but ascending is not started yet. So, again he is stationary. So, both of these points are stationary. And at both of these points, first derivative of the function will become 0. So, first derivative of the function 0 at both the points. So, that means by taking first derivative equal to 0, you can only find the stationary points, not the maxima and minima. You cannot decide whether that stationary point corresponds to maximum value or corresponds to the minimum value, whether it's a peak or it's a valley. You cannot decide from first derivative equal to 0. The same thing, by saying force equal to 0, you can say only equilibrium. Equilibrium means net force 0, that is the stationary in physics. But you cannot say whether it is a peak of the potential or it is a valley of the potential. Valley of the potential means minimum potential, and peak of the potential means maximum potential energy. Clear? Now, why I emphasize with the first derivative with the force? Because potential energy's first derivative will be force. Because we know that, suppose you know that potential energy for a spring is half kx square. Take the first derivative of potential energy. du dx. It comes out what? Kx. Now take negative of this, means Hooke's law, F. This is the force. For a spring force, Hooke's law, F equal to minus kx. So negative derivative of potential energy means force. So that's why we are emphasizing that first derivative and the force equal to 0 and force equal to 0 are similar, because force equal to 0 means potential energy's first derivative will be 0. So from that you can only consider where potential energies are maximum or minimum, those stationary points where maximum and minimum lies. But you cannot say which one is maximum or which one is minimum. For that to decide, we require the second derivative. Okay? Now, is this concept clear? Because this is a very important concept in physics, and this is a concept of coming from the mathematics. Most of you think that mathematics is very bad subject and it is not at all required for doctors. But remember, this, without this you cannot solve the physics problems. And I don't believe that doctors are very bad in mathematics. Suppose you have to operate, you have to cut 3 millimeter, and doctor is unaware of the measurement, units and measurement or this. He cut like this. Okay. See. So now we have to check the second derivative. How? Now many of you have the confusion that you studied already that at the maximum value of a function, near the maximum value, the double derivative will be negative, and near the minimum value double derivative will be positive. Now it creates bit confusion that near the maximum it should be positive, near the minimum it should be negative. Normally people believe that, but that is not true. Why? See, this is a stationary point. So just before this, reaching this stationary point, I want to draw a tangent. Now tell me, if I calculate dy dx at this point, is it positive or negative? It is positive. Why positive? Because see, if you extend this, it will cut the x-axis at an acute angle. Acute angle means tan theta will be positive, because in the first quadrant all trigonometric ratios are positive, so tan theta is also positive. So dy dx is positive, means greater than 0. Just after this stationary point you draw another tangent and check whether at this point derivative, what is the sign of the first derivative? See, it will cut at an obtuse angle, means in the second quadrant. In the second quadrant tan theta will be negative. So at this point dy dx is negative. Okay. So I denote this one as dy dx initial value, and this is dy dx's final value. Dy dx final minus dy dx initial. Now just check dy dx final minus dy dx initial. What is the sign? Final minus initial means change in dy dx. Final value is negative, initial value is positive. Suppose final value is minus 2, initial value is plus 2. So minus 2 minus 2. So it will be negative. So negative, from a negative value you are subtracting a positive value. So entire value will be negative. Now what you are calculating? Final value of the dy dx minus initial value of the dy dx, means you are calculating change in dy dx. So what is dy dx? Change in y with respect to x, and you are calculating its change. So change of change. Change of change means double derivative. Change means first derivative dy dx. You are calculating the change in the first derivative. Change in the first derivative means second derivative. So that's why we are saying that d2y dx2 less than 0 near a maxima. dy dx initial minus dy dx final. dy dx itself means change in y with respect to x, and you are taking the change in the derivative. So change of y with respect to x. So change comes twice. So it is second derivative.